Let's look at a couple more examples of problems that can be solved using the decreasing annuities formula. So imagine that we know the present value. In this problem, we're going to start with $5,000 in the account, and we're going to make withdrawals at the end of each month as the account earns interest, 6% annually, and we want the money to last 20 years. How much can we withdraw each month? Well, we don't know what the monthly payment is out of this account. That's what we're trying to find out. We do know the present value is $500,000. We know that 20 years of payments, 12 payments a year, will be 240 payments. And we have a periodic interest rate, 6% divided by 12. Plug all of that into the decreasing annuities formula that we see at the top of the screen. And the quantity we're trying to isolate, PMT, is isolated if we just divide both sides of the equation by the big expression in parentheses. You can then plug that into your calculator and you end up with approximately $3,582.16. So this is the sort of calculation that can tell you, once you reach retirement, you know how much money you've put away in an annuity earning a certain interest rate, how much you can withdraw if you want your savings to last a fixed amount of time. Another question you might wonder is how long the savings will last if you instead already have chosen how much to withdraw. So in this problem, we imagine we're going to make payments out of the account of $2,000 at the end of each month. Again, our account will earn a 6% annual interest rate, and this time it only starts with a balance of $200,000. How long will it take before you drain this account? Our payment size is $2,000. Our starting present value is $200,000. We don't know how many payments will be made. N is the variable we will need to solve for. And we know the periodic interest rate is 6% divided by 12. Plug everything we can into the present value formula. And the unknown we need to solve for is N. N is in the exponent, so we can expect to need to use logarithms in order to solve for the variable in the exponent. Let's start by simplifying. We can do a little bit if we just divide both sides by 2,000. And then we can multiply both sides by 0.005. That gets rid of the denominator we had on the right side of the equation. Then I can subtract 1 from both sides. And I can change both of those negatives into positives if we multiply both sides of the equation by -1. And now we're ready to apply a logarithm formula. If we take the log of both sides, then we can bring the exponent -n out front. And now we'll be able to isolate n if we divide both sides by negative log of 1.005. That gives us an expression we can plug into a calculator. 138.98 approximately. Now notice that's almost 139. So it'll take approximately 139 months to empty this account. The fact that we got a number a little bit less than 139 actually means this. The amount of money we withdraw the very last month will actually be slightly less than $2,000. That very last withdrawal will not quite be $2,000 because the interest rate was not quite enough to empty the account. If we'd gotten something just a little bit more than 139 instead of something a little bit less, that would have told us that we were able to withdraw $2,000 at the end of the 139th month, and there was still a little bit left, so that you could actually have another withdrawal of a tiny bit in 140th month. Now, that's not the case here. The fact that this number is a little less than 139 means You'll get 139 withdrawals, but the last one will be a little bit short.